Okay, whenever you see a problem like this, you know it's what kind of a problem? It's a factoring problem.
Okay, factoring.
Yeah, because everything here, this numerator can be factored, this denominator can be factored, this numerator can be factored. So the trick is to factor everything and then see what cancels out. So factor the numerator for me of the term on the left.
All right. 4 and 1 should be x plus by 4 plus by 1.
And the denominator?
1 and 1 plus by 1.
And then the term over here, factor the numerator here.
Would just be x in the parentheses. Oh, x plus 1.
All we're doing is factoring a 2 out. Okay, and this x plus 4 can't be factored, so we leave it the same. Now it's a game of cancellation. Okay, let's start canceling. We can cancel that with that. We can cancel that with that. We can cancel that with that. So what are we left with?
Just 2.
I mean, when I say cancel, I'm replacing that with a 1 in all cases. But yes.
Since they're all 1s, it would
exactly.
equal to.
So the moment you see a problem like that, just know it's just a factoring problem, and all that stuff's going to get canceled.
Okay.
35.
All right.
This, whenever you see quadratics, they probably need to be factored. In other words, we don't have to solve this by factoring the denominator, but it's probably going to be easiest. Without knowing anything more about it, my first step is going to be factor everything I can see.
All right. Oh, 3 and 2. X plus 3 and x. 2.
Okay. How about this one over here?
Two and 2. X plus 2.
Okay. What's a common denominator going to be? Now, I can't cancel this x plus 2 with this x plus 2. But I can figure out what a common denominator is going to be.
Could I times the left side by x plus 2 and then times the right side x plus 3?
Yes. And in fact, you don't really need to times the left side by x plus 2 if you think about it.
Oh, because
x plus 2 divides into that evenly. So here's going to be my common denominator. I need an x plus 3. I need an x plus 2. No, you're right. I need 2 of these. I don't know what I was thinking. So there's my common denominator, but I don't need to multiply this whole thing by that whole thing. Otherwise, I would have 3. I would have an x plus 2 cubed. And I don't need to do that because this is a lower common denominator. And I know this works because this divides into it evenly and this divides into it evenly. So I know that that's going to be my common denominator.
Yeah.
And what's the rest of it? What's the top left?
Oh, it's going to be 2x.
Say it. You're just getting ready to say it.
2x plus 4.
How about over on the right?
X squared minus.
What do we have to do to this fraction in order to get this denominator?
Oh, we had to times it by x plus 3.
Okay. So what's the new top?
X squared.
No, it's going to be x minus 1 times
and then
plus 3.
Oh, okay. Yeah, sorry.
It's okay. In other words, what I did was this.
Yeah.
Okay. All right. So now it's just a question of simplifying and distributing the top and see what we have. Well, let's FOIL these two together first. And one thing you want to make sure you do here is make sure this negative sign applies to everything in the numerator. In other words, put an extra parentheses around that. It's probably the biggest single error that people are going to make on this problem.
All right.
Okay, so I'm going to put parentheses there. Now FOIL these two.
It's going to be x squared plus 3x minus 1, or plus 2x, I guess you could say.
Okay.
Yeah, and then minus 3.
Okay. Let's simplify all of that. Starting with the highest degree.
X squared.
Minus x squared.
Or minus x squared.
Okay.
Plus by 2x. Or minus 2x.
Well, I got a
Yes,
2x over there and a minus 2x here. I don't have any x's left.
Oh, so just, okay.
Okay, but I got a number.
1? Or 7? Plus 7.
Yeah, there you go. Okay, so that's my answer is this divided by that. And there's nothing more I can do to it.
Okay.
Okay, I can't simplify it anymore. If somehow I could extract an x plus 3 or an x plus 2 out of this, I would and then cancel it, but I can't.
Okay.
Okay. Okay, and this last one here. Let's see. Let's write it out. And as I'm writing, I'm going to factor because I know that that's always a good step. Okay, now this is one of those problems where you do that magical first step and it cleans up the whole problem big time. What's the magical first step? To get rid of all the denominators in one fell swoop. What would I have to multiply both sides of the equation by? before we do anything, let's simplify this. What can I do immediately right here?
Cancel out the x.
Okay. Makes the problem a little easier. Not really. I still want to multiply. I still want to take the same first step that I was going to take.
Let's see.
Think of it as finding a common denominator between all three denominators.
Yeah.
What would that be? And I'm going to multiply both sides of the equation.
Right.
There's the common denominator that would result, right?
Right.
But we're not going to solve this. We're not going to solve it by finding a common denominator. We're going to solve it by multiplying both sides of the equation by this term.
By x.
Watch what happens.
Wait.
Very beautiful
How do you...
things happen. Go ahead. Now I have to multiply this term also by it. In other words, I really need parentheses around that whole thing like that.
Yeah. How? Where did you get the x and the x plus? Did you just take them?
By finding the common denominator between those two. Actually, between those three.
Common
denominator would be the product of all of them. But I don't need to do x plus 2 squared. I can multiply both sides by x times, find a common denominator that is going to get rid of every one of these denominators in one step.
Yeah. I didn't know how to do that with
this will do it. This will do it. What's it leave here? Cancel that and that. What do you got left?
Oh, you can just do that. 4x plus by 8.
Yeah, that's the whole point in doing it, is to get rid of the denominator. Now what are we going to have here?
Okay, I didn't know how to do. I didn't know you could do that.
Yeah,
all right,
it's a super slick thing.
So it'd just be, that would cancel out and it'd just be left with 1, right?
X. I got this x. In other words, I didn't cancel this x for this term here.
Oh, okay.
Remember that I have to multiply this common denominator by both. If I'm going to multiply both sides of the equation by it, then I have to multiply each term of each side of the equation by it.
Yeah,
so I multiplied this by this and got 4x plus 8. Now I'm going to multiply this by this over here, and it just leaves x. And then when I do the right side of the equation, this cancels, that cancels, and I have just x over there. So there's what I have left, and that is so much easier to solve. That's why this first step is such a beautiful step, is that it allows you to clear out all the denominators at one time.
Okay.
Okay, so 4x equals negative 8. X equals negative 2.
How does that?
Go ahead. How does it do?
How does that x plus 2 not cancel out the x plus 2 on the?
It did.
The denominator.
You're talking about this one here and this one?
Yeah, on the left. Yeah.
Yeah, it did. And that's why we were left with just x.
Oh, okay. Gosh. Okay, I got you.
Okay.
X times the. Okay.
Right. In other words, this was our left term, this was our second term, and this was our term on the right side of the equation. But the secret in finding this thing is to kind of think of it as looking for a common. In other words, the other way to solve this problem is to do it normally. The normal way to solve this problem would be to find a common denominator, right?
Yeah.
Well, that common denominator is going to be x times x plus 2. This top part will be 4 times x plus 2. This top part will be just x. Over here, we won't do anything, but we can certainly divide both sides of the equation or multiply both sides of the equation by x plus 2. So now we eliminate it to that. Now we have to multiply both sides by x, so we get this. So we eventually get to that same spot, even if we treat it as adding fractions.
Okay.
Notice that there is a big difference between adding fractions and multiplying both sides of an equation by something.
Yeah.
I can multiply both sides of an equation by anything I want. It doesn't matter as long as I do it to both sides. If I'm changing a fraction, I can't just do anything I want to 4 over x, but I can multiply it by the number 1. So I can multiply this by x plus 2 over x plus 2 to get that common denominator, but that's it. I can only multiply a fraction by the number 1. But I can multiply both sides of an equation by anything I want.
Okay, I wasn't sure if that plus in there equaling, I don't know, I've never done that.
Yeah, if this was x plus 3,
That was x plus 2.
I know, but if it was x plus 3,
Oh, if it was x plus 3.
yeah, then I would want to multiply everything by x. Then this would get rid of all denominators in one step.
All right.
But I would have to multiply every term on both sides of the equation by this.
Yeah, that'd take a while.
Well, not really. It still gets rid of the denominators. And the denominators is what presents people with problems when you're solving algebraic equations.
Yeah, it'd just be messier.
As long as you get it down to all numerators, everybody can do that. So the trick is to get rid of the denominators as quickly as you can.
Okay.
All right. Is that all you got tonight?
Let's see. I think I have some graphs that here. I'll take some pictures.
Did we? You know what? I just realized I didn't do the right one. There was a 2.
X.
Oh no! After I factored out. Oh yeah, I factored out the x and then canceled it with that.
Yeah, you did that in the first.
Okay. Yeah, yeah. No, we did that right. We did that whole thing right. Now, let's see. You have another session scheduled for tomorrow night at 5:30.
Yeah, and I don't think I'll actually need that, to tell you the truth.
Okay, let me go ahead and cancel it right now.
Let's see. I have about 2 more problems Friday night.
Okay. Sounds like most of this stuff can be verbalized.
Yeah. So this is just graphing a simple rational function. So
Okay.
be y equals x plus 1 over x minus 3. And then just need to graph it and find the equation of asymptotes in the domain and range.
Okay.
So,
What kind of a graph will this look like? What's it called?
sorry?
This is called a hyperbolic graph?
Hyperbolic.
Uh-huh. In other words, the parent function is y equals 1 over x, which graphs like this.
Mm-hmm.
Those are hyperbolas.
Okay.
Okay? Now, the key is that it's not going to be about the x and y axis, and it may not be quadrants 1 and 3, it may be 2 and 4. So
Okay.
that's all we have to determine. Now, the first thing we want to figure out is what the vertical asymptote is, because that's going to represent one part of the grid that you're going to draw this hyperbola in.
Mm-hmm.
So what's the vertical asymptote? What makes the denominator 0?
Oh, 3. X equals 3.
That's always the vertical asymptotes, or whatever makes the denominator 0. So that's our vertical grid that we're going to draw this thing about. What is the horizontal asymptote?
X equals negative, or Y equals -1.
Y equals +1. It's the ratio of these coefficients. In other words, if the power of x is the same in the numerator as it is in the denominator, then the horizontal asymptote is the ratio of those coefficients. If the denominator is bigger power than the numerator, then the horizontal asymptote is y equals 0. But in this case, the horizontal asymptote is y equals 1. So there's our dotted line grid that we're going to create this hyperbola. And it's either going to look like this. That's one possibility. The other that's in quadrants what I call 1 and 3. The other possibility is it could be in quadrants 2 or 4. 2 and 4. So all we have to do is find one point on this graph and we'll be able to determine what it is. So pick an x value to the right of the vertical asymptote and let's figure out what y is. Put that point on there and that'll tell us which quadrants we're in.
I'll go 4.
Okay. What is y when x is 4?
5.
So the point that's on the graph, that's a point on the graph, right?
Uh-huh.
That tells us it's first and third. That's all we need. Now, this hyperbola is asymptotic with these asymptotes. In other words, as x goes to -infinity, this approaches the line y equal 1, and as x approaches 3 from the right, this approaches +infinity. But as long as we know that that's a hyperbola, and it's basically pretty straightforward figuring out your vertical and your horizontal asymptote and figure out which quadrant you're in.
Yeah.
Now, it can be a little more complicated if it has two vertical asymptotes. If you start with a grid like that, then your answer usually is asymptote or hyperbola up there, and then something maybe like this in the middle, and then that on the left, if it's a real complicated function. In other words, if I had a function that had a denominator of x minus 3 times x plus 2, how I would graph that, well, that has two vertical asymptotes. So I would start with drawing those two vertical asymptotes as a horizontal asymptote at y equals 0. So my basic grid to graph that function there would look like this. There's my two vertical asymptotes and my horizontal asymptote, which is now at y equals 0.
Okay.
Okay?
Then do you just have to pick a point on each side?
Well, kind of. In other words, actually figuring out how to graph that whole thing is harder. There's a lot more to it. It's not just domain and range. You kind of, well, it is kind of domain and range, but you may not get any that hard.
Yeah, I don't.
Yeah, let's go back and look at the one we were just looking at, because they wanted domain and range also. Okay, here was the curve. What's the domain? This is y equal x. What was it? X plus 1 over x minus 3?
Yeah.
What's the domain from the graph?
It'd be infinity or negative infinity.
To what?
To 3.
In combination with?
Infinity to, or negative, oh yeah, 3 to.
In other words, you go from negative infinity right up to 3, but not including it. But then you can pick up to the right of 3, but not including it, and go all the way to positive infinity. So what's the range?
Negative infinity. All the way to 1. And then 1 to positive infinity.
Okay. Now, a true statement is that functions can never cross vertical asymptotes.
Okay.
Also a true statement is functions can sometimes cross horizontal asymptotes. In other words, there's a possibility.
Uh-huh.
1 second.
Okay.
Hello? Yeah, Thomas. That's fine. I'll see you at 8. Okay, bye-bye. Okay. In other words, it's theoretically possible with the right hyperbolic function that this could do something like this. Actually cross that and then come back and be asymptotic with it. And that would actually change your range.
Yeah. Oh.
The range would now be negative infinity to positive infinity.
Oh, okay, please.
This is probably beyond your level of degree of difficulty at the moment. They probably aren't going to give you these. But
yeah.
The way you would determine that is there a value of x that makes y equal to 1? In other words, can you solve the equation 1 equals x plus 1 over x minus 3? And that will tell you whether or not it crosses that horizontal asymptote. Notice if you try to solve that, what you get. You get x minus 3 equals x plus 1. X's cancel. You get minus 3 equals 1. That can't happen. So this thing can never cross that asymptote.
Okay.
It would have to be like this.
All right.
But there's also oblique asymptotes that look like this. Okay? And if you have an oblique asymptote, that also can be crossed. That is not inviolable. Most of the time, if you have an oblique asymptote like this, your graph looks something like this.
Okay.
Okay.
And that would be...
Yeah, let's just stick with your problems because I may be showing you stuff that is they're not going to do to you. Do you have another?
Let's see. think actually, here, one sec, yeah. Y equals x squared minus x minus 6 over x plus 1.
Okay. In keeping with my previous statements, let's factor the top.
Alright, so
Biggest reason to factor it is there may be an x plus 1 in it. But there isn't.
yeah, it'd be x minus 3x plus 3.
Okay.
2, oh, to get the negative 1. Oh, yeah.
So if we go to graph that, where do we start?
We gotta put 1 at positive 3.
Well, no, you always start with your vertical asymptote.
Okay, so it'd be at 1.
Negative 1.
Or negative 1.
So here's my starting spot. Now the rest of it gets a little complicated. I'm kind of surprised they gave you this. When the degree of the highest variable is greater in the numerator than it is in the denominator, there's a first step.
Okay.
Do the division.
Oh, all right.
Do you know how to do this division?
Yeah.
Okay, what do I put here?
It'd be x.
And then what down here?
X squared plus by 1, or plus by x.
In other words, you're going to multiply this term by both terms.
Okay.
And then subtract, just like you do in long division.
Should be negative 2x.
And then bring down the 6.
Yep.
And then do the process again.
Negative 2.
Right. And now
Minus.
continue until we get a remainder. What's this?
It'd be 4, or negative 4.
Negative 4. So now we're ready to say what this is. This is x minus 2 plus, or minus, plus a negative 4 divided by x plus 1. You see how we get all that?
Yeah.
Okay, this part of it is the oblique asymptote.
Okay.
How would I get? That's a straight line. In other words, y equal x minus 2 is the oblique asymptote. Well, how would I graph that? I would go to the minus 2. It's got a slope of plus 1. So there's my graph. And for the oblique asymptote, I ignore the remainder.
Okay.
But to plot it, I can't ignore the remainder. Let me think for a second what we have to do here.
Is that okay?
Well, this is going to plot one of two ways. it's going to look like, I'm going to draw the two possible ways that this could graph. Remember that the graph has to be asymptotic with these asymptotes.
Yeah.
Okay, so it's got to look something like this. And then, see that?
Yeah.
Or, in other words, that's first and third, kind of. If you want to think of it as first and third quadrant. Or it can be like this.
Huh. All right. On each.
In other words, very similar to the hyperbola. It can be second and fourth or first and third. So
Okay.
let's figure out where. What did I have? I had y equals
X minus 3 and X plus 2.
all over x minus x plus
plus 1.
Okay.
Yep.
All right. So let's pick a point far to the right, well, not too far, but to the right of the vertical asymptote and figure out what the y value would be.
Should I just pick 0?
Yeah.
All right. Should be negative 3. 2. Should be negative 1 over. Should be negative 1.
No, if you're going to fill in 0 for x, then we have negative 6 over 1, which is negative 6. So when x is 0, y is negative 6.
Oh, it would be negative. Oh, yeah, because your times in. Okay.
Okay.
I added that.
So this point right here is on the curve. 0, comma, negative 6. Well, that tells me almost everything I need to know. That means the curve looks like this. Now, here's the problem, is domain and range is not, let's see, domain is very clear-cut, and range is clear-cut. There's no problem with domain and range at all. In other words, there is no horizontal asymptote on this.
Okay.
Because the power in the numerator was greater than the denominator, is all we had to find was the equation of the oblique asymptote along with the vertical asymptote, and then figure out which quadrants we're in. Now, for this problem, domain is what?
Negative infinity to negative 6.
To negative 1. Remember, domain is going along the x-axis.
Oh, okay.
In other words, you get to this vertical asymptote, which we cannot cross. So the domain is going to be negative infinity to negative 1 combined with negative 1 to positive infinity.
Infinity, yeah.
Range is what?
Would have been negative infinity to to negative 3?
No. Range is
negative
y.
6?
When you're thinking of range, just pay attention to the y values. Is there any y value that this function cannot be?
No.
So the range is all reals. Negative infinity to positive infinity.
Okay.
Because there's no horizontal asymptote. So there's no barrier.
Okay.
Okay?
Oh, gosh. All right. Yeah, that makes sense.
Okay. Now, sometimes these can be difficult problems when there's an oblique asymptote. And let me draw you the case where it would present problems. And that is if we had drawn this thing this way, in other words, if it would have been turned out to be in these quadrants, notice there's a big problem now.
Oh, yeah, it crosses the vertical asymptote.
Well, no, that I didn't mean to do that. That was accidental. The problem is the range.
Oh, there is no. Yeah.
Well, there's a range, but in order to figure out the range, we need to know that maximum and we need to know this minimum, because it does not attain a value in between.
Yeah.
The range would be negative infinity to this value, and then this value to positive infinity. The problem is that finding this value is not the easiest thing in the world. That almost requires calculus. And in fact, would require you to use your graphing calculator. You'd have to graph the function, and then you'd have to put it on trace and figure out what that value was for that maximum right there.
Yeah.
And that would be part of your range.
Yeah, that would.
So those can be very difficult when it's in those two quadrants.
Okay. And that was an oblique.
This is called an oblique asymptote, and this actually can be crossed. In other words, theoretically, well, we were this way and this way, but this theoretically could have crossed that and come back on it. In other words, you can cross oblique asymptotes.
Okay.
So I wasn't 100% sure of my graph, whether I was doing it right, but it didn't really give us a better way of graphing it.
Yeah.
What else?
I think that's it for.
Okay.
Yeah, that was pretty much the hardest one that we had. So.
Okay. Well, it sounds like this might be our last session.
Yeah, I think so.
Okay. Well, good luck to you. And,
yeah, thank you.
Yeah, if you need help next year, you'll be taking what next year? Pre-calc?
Yeah, probably.
Okay. You'll either probably take pre-calc or college algebra.
Yeah, I think I might be taking college algebra, actually.
Okay. Well, either one of them you might need help on, and certainly feel free to contact me.
All right, sounds good.
It's been a pleasure working with you, Alex, and good luck to you. Have a good summer.
Yeah, thank you for all the help.
Sure. Talk to you later.
Yeah, talk to you later.
Bye.